Hello, for today's video lecture, we're going to be looking at rigid body surface impacts. So, when a rigid body impacts a surface, it has the potential to bounce off the surface just like a particle, but there's also the potential for rotation before or after the impact, complicating the situation. So, for example, if we dropped a wrench on the floor, we could imagine that, maybe even if we drop it straight down, it's going to impact the floor, and after that impact, it's not only going to have a bounce, where it bounces back up, but it might have a rotation that it didn't have before the impact. So we've got this added piece of rotation that can happen before and after impact, and it's going to complicate our regular surface collision circumstances. So with a rigid body surface collision, we're often going to be given a set of velocities before an impact, and we'll need to solve for the velocity of the center of the mass after the impact, which can include components in this case. So we can have normal and tangential components after the impact, or we could have x and y components. And we're also going to have this angular velocity of the body after the impact. So we've got kind of three unknowns. We're going to have the normal velocity after the impact, the tangential velocity after the impact, and the angular velocity after the impact. So three unknowns means we're going to need three equations to work with to solve for these three unknowns. All right, so in order to generate three equations, we're going to need to rely on the normal and tangential directions just like we did with particle surface collisions. So we have the tangential direction, which is going to be parallel to the surface, and the normal direction, which is going to be perpendicular to the surface, and it's going to be the direction of the impact forces. So the impact force is always going to be perpendicular to the surface, just like the normal direction. All right, assuming that there's no friction force during the impact, there's no force at all to change the velocity of the body in the tangential direction. So this is specifically going to apply to the center of mass of the body, and therefore the mass, or the velocity tangential of the center of mass final is going to be equal to the velocity in the tangential direction of point C initial. This velocity in the tangential direction of our center of mass remains unchanged before and after impact. So next up, we've got the coefficient of restitution, which can be applied in the normal direction. So this is going to be applied specifically at the point of impact on the body. So the coefficient of restitution is going to be equal to the velocity of point A, which is our point of impact, in the normal direction final, over the velocity in the normal direction of point A initial. So we've got a negative in there because it's always going to change directions. If it goes in, it bounces off the surface, it's going to have the opposite direction after the impact. So the higher the coefficient of restitution is, the more bounce we have. An elastic collision is a perfect collision. Our coefficient of restitution will be 1. And then any semi-elastic collision, which is most real collisions, are going to be somewhere between, the coefficient of restitution is between 0 and 1. All right, so our third equation is also related to the coefficient of restitution. So it can be used to also relate the kinetic energies before and after the impact. And our coefficient of restitution squared is going to be the final kinetic energy divided by the initial kinetic energy. So it is important to note in this, the kinetic energies should include both translational and rotational kinetic energies. So even though the wrench comes in, maybe it only has translational, it's got 1/2 mv squared. If it bounces off the surface and has rotation, it's going to have 1/2 mv squared plus 1/2 I omega squared after the impact. All right, so putting this all together, we have three equations that should allow us to solve for up to three unknowns. We've got the velocity in the tangential direction of our center of mass does not change. It stays the same before and after impact. We've got the coefficient of restitution, which is going to relate the velocities in the normal direction at our point of impact before and after the collision. And finally, we've got our coefficient of restitution squared, which we can use to relate the kinetic energy final divided by kinetic energy initial. So these equations will sometimes need to be supplemented with kinematics relationships. In this case, we might need a relationship relating point A, so the point of impact, to the velocity of point A to the velocity of the center of mass and angular velocity. And that simply becomes a kinematics problem. It's going to vary based on your situation, but you've got kind of rotation and translation, so it becomes usually a relative motion problem in this case. All right, so going through this whole thing, the process you use for a surface collision. So we have to carefully account for factors at play between some initial state and final state, usually it's before and after impact. We're going to set up a diagram showing the object bouncing off the surface, identify any known and unknown velocities in each state, including magnitudes and directions. It's going to let us break it down into normal and tangential components. You want to identify the type of collision and, if possible, the coefficient of restitution. We want to identify the normal and tangential directions clearly in our diagram. So once we get our diagram set up, we can set up our equations. So use the equation to break down velocities into normal and tangential components. And use the three equations we discussed earlier to relate those initial and final velocities. Supplement this with kinematics relationships as needed. Again, kind of relating the velocity of point A to the velocity of the center of mass and angular velocity. And then once you have all that set up, solve your equations for any unknown quantities. All right, that's all we have for today's video lecture. Thank you for watching, and I hope to see you again.